Does anybody have homework questions today? Yes. So we looked at this in class on Monday, I think it was. If you take, maybe it was in my other class, if you take a huge number of sheets of paper, each piece of paper is two-dimensional. So you can think of a piece of paper being a plane. But if you take a huge number of pieces of paper and stack them up, well, then you have a shape like your textbook. Okay, so your textbook has not just two directions, it has thickness too, not just vertical and horizontal direction, but also thickness or up. So that you take two dimensions and stack them up and you get three dimensions. And since we learn by analogy between dimensions, the idea is that if you take a huge number of 12-dimensional spaces and stack them up, you get a 13th dimensional space. One dimension higher when you stack up the spaces. Yes? 7.1? So I will probably, the 7.2 won't be due this Sunday after all, because we didn't get to the material yet. So whatever we cover today will be on the Wiley due this Sunday night. But I'd like you to have time to go over questions. So 7.2 will be a topic we cover on Friday, and then you can ask questions Monday, and I'll push the due date up a week, okay?
So 7.3 can you change to?
Oh, it's 7.3? Yep, then I'll change 7.3 as well. Let's see what it says for due dates. Okay, so just 4.7 and 7.1 will be due this weekend, and the other two will be due the following weekend. Any other questions? Before we move on to Chapter 7, I'd like to answer the questions that you asked about the fourth dimension when we first started talking about the fourth dimension. So the first question you had was, and here's a reminder, study group tonight, okay? Or one-on-one tutoring, and that can be done through Skype as well, that one-on-one tutoring. This won't be Mondays again unless you meet one-on-one with the tutor. So the questions that you had about the fourth dimension, you'd asked about what the fourth dimension is. So hopefully now you have a better feel for that. The fourth dimension is a dimension that would be perpendicular to the three dimensions that we live in. But because we can only see three directions, it's not readily accessible to us. Although the mathematics behind the fourth dimension, mathematicians use all the time on a regular basis. Mathematicians and scientists too will add a fourth or a fifth or a sixth variable into whatever they are describing that needs that many variables, and that when you do that you are working in the higher dimensions. What does it look like? We can only see that by analogy, so hopefully looking at flatland, going to three dimensions, you being in three dimensions looking at flatland gave you a feel for what it would be like to be in the fourth dimension looking at the third dimension, but I'm not able to actually take you there. Can you draw in the fourth dimension? Well, you can draw a cube in the fourth dimension. So you remember what we do? We just ink up what we draw in the third dimension in three dimensions and drag it into the perpendicular direction, and that's how we simulate drawing in the fourth dimension. Are we in the fourth dimension? We live in the third dimension. The fourth dimension we perceive is about us. That's what the current theories of the universe tell us. And so even though we exist in the third dimension, the fourth dimension is about us. Just like three dimensions look down at flatland, right? Okay, so the third dimension surrounded flatland in 2 dimensions. So in that sense, flatland is in the 3 dimensions. It's just not accessible to the 2 dimensions. In the same way, the 4th dimension would be about us in a perpendicular direction that we cannot access. How do 4D movies work? Who knows? What do they do in a 4D movie? I haven't been to one for many years. When I went, it was at Noah's Ark, and the chair in front of you squirted water at you. Yeah, like that, and then they shook it a little bit. Okay, so I think the 4D movies are adding, how would you describe that? Some physical component to the experience of watching the movie. Anybody have any other questions about the 4th dimension? Then we're going to move on to an area of math called fractals in sections 7.1 through 7.4. Fractals are a relatively new area of mathematics. A couple of our professors here have studied fractals very intensely as their area of interest. So our question here, 7.1, how can you convince your parents that you're eating enough broccoli? Well, that's a kind of strange question. Here's the picture that your author is looking at. So what your author does is he says that you can convince your parents you're eating enough broccoli by sending them the picture on the right. So there's 3 pictures here. You see how they're very similar to one another? If you were to put them all in one picture, this is what you'll have. So you have the little bunch on the right, then the medium bunch and the left-hand bunch. So what your author is getting at here is a fractal sense of self-similarity. So fractals, these are fractal-like objects. They have a sense of self-similarity. The little piece is similar to the medium piece is similar to the big piece. Here's a man-made fractal that shows that that sense of self-similarity. So this one is called the Sierpinski triangle, and we're going to learn to draw that in section 7.2. So you can take this piece, for example, and if I covered up the rest of it, then you wouldn't really know that I'd covered it up. You'd say, oh, there's the Sierpinski triangle, because it has a sense of self-similarity. This piece is like the whole piece, or this medium piece is like the whole piece, or this little tiny piece is actually like the whole piece. This is, if you have a computer-generated fractal, then there's infinite detail, and you could keep zooming in and it would keep looking like itself. Here's another real-life example of self-similarity that a fractal would exhibit. So you see, have you seen this? Only this is usually with Quaker oats, right? You got Quaker oats and you have the image of the image of the image. We have this at the beginning of class when I'm setting up the recording monitor. So on the recording monitor, if I could keep zooming in and in here as well, you would still see more of the same. So a fractal has a sense of self-similarity on a smaller scale. Another real-life example of an object with a sense of self-similarity would be a fern. Okay, so if you look at this whole fern, you can look at a single leaf, and the single leaf looks like the whole fern on a smaller scale. Or even within that leaf, you can take a little tiny subleaf, and that subleaf looks like the whole fern on a smaller scale. How about my marker? Does my marker have a sense of self-similarity at all? No. Does it have infinite detail? No. Marker's not like a fractal at all. It has no sense of self-similarity. no infinite detail. I have weird things in my box. This little piglet, this little piglet is here for a different application in another class. What does that little piglet exhibit? Any fractal-like characteristics? Does it have any self-similarity or infinite detail? No, it doesn't have a little pig inside itself, right? It's just its own little thing. We're going to look at some of these pictures in a minute together. I'll go ahead and grab it now. So let's write down the definition of a fractal as best we can. There's actually not a formal definition of a fractal. Mandelbrot is the one who brought us fractals initially, and he used several descriptions. We'll look at two descriptions of fractals. So I'll call these informal definitions, because this is one of the areas in mathematics. There's not very many, but this is one of the areas where we don't have a formal definition. Fractals are infinitely complex patterns I feel like I maybe should drop the E. Who's the spelling person? Is there an E in infinitely? I feel this rule coming back to me. Drop the E and add ly. Anybody know? Nobody knows. Do you know?
I think you keep the E. Yeah.
You think you keep the E?
Yeah.
Okay. Fractals are infinitely complex patterns that are self-similar across different scales. That are self-similar across different scales. They may be created by repeating a simple process over and over. By repeating a simple process over and over in an ongoing feedback loop. Now that's one informal definition, and I think it's especially nice for computer-generated fractals, because you see that infinite detail in a computer-generated fractal. We'll look at one example in a minute. One of Mandelbrot's definitions, he had a shape made of parts similar to the whole. Similar to the whole in some way. A shape made of parts similar to the whole in some way. And that, I think, is a particularly nice one for natural occurring fractal-like objects in nature. For example, a tree. Okay, you look at a tree, right? Okay, this is terrible. I think we've already established art's not my best thing. Okay, but if you took a branch off a tree and you held it up next to a tree, it looks very similar. It looks like a small tree. And sometimes you can break the twig off the branch, and that looks like a small tree as well. So you can get a smaller and smaller version of that tree. And we saw that in the fern, okay, when we saw the fern made up of little pieces, and then each little leaf had little pieces. Oh, that's terrible. Let's look at the book's picture of the fern for that. Oh, can anybody think of some other real life examples of fractal-like objects? Yes. What's what? Broccoli. Broccoli would be another one. Good. Okay, so these are questions that I will ask you on a quiz to name a real life fractal-like object, something that occurs in nature. Now, the computer-generated fractals are used in creating scenes for movies often. So here I have some examples of that from section 7.2. So on each of these pictures, we have a real-life photo next to a fractal. Did anybody see the moon Monday night? It was beautiful like this. Yeah, it was beautiful, wasn't it? Okay. So does anybody want to guess which one's the fractal here in this image? Which one's the real photo and which one's the computer-generated fractal? Yeah.
The right one is the real one and the left one is the computer-generated one.
You know, I think I would have guessed that too because of the stars, but actually the one on the left is the actual photograph.
Oh.
Yeah, I know, it's close, isn't it? Okay, here's 4 more. So in each case, one is a real photo, a regular photo, and one is a fractal, computer generated. So we're not seeing the self-similarity in the fractals in this case, but what we are seeing is the infinite detail. So if we were to zoom in on the one that's a fractal, we would see infinite detail. And I'll show you an example of that in a little bit. Okay, so did you decide which one is the real photo? In both of these, it's the one on the left. The left one is the real photo. The one on the right is computer generated using a fractal process. One more example, and again, the left one is the photo. I think the right one does look computer generated more this time. No, maybe not. So in this section, we want to become familiar with the idea of what a fractal is, and we want to be able to make some fractals. So later on in section 7.2, we'll be making fractals. For now, I wanted to give you another feel for how these have infinite details. So I have an app for both Apples and Android. So if you have your phone and you don't mind downloading a free app, we'll look at the Apple one first. Okay, so those of you who have Apple product, I don't know if this is available on the Apple computer or just on the Apple store. So this is the Fractal Factory. So it's the Fractal Factory. I don't know if that's enough for you to find it. Anybody find it? Should I see if I can find it in the store? Okay. So Fractal Factory. So it's this one, yeah, it's this one right there. Okay. So you can experiment here. There's sliders. There's sliders up here if you choose one of the different sets, and you can. In 7.4, we'll see how this Julia set is created. This is the Julia set. I have my slider set to 0.32 for the top slider and 0.44 for the bottom slider. Anywhere around 0.32 and 0.44 makes really beautiful pictures. So you just move the little bubbles left and right. Once you've set it somewhere near there. I think you might even be able to just type on the number. Yeah, you can type the number. If you press on this number up here, you can type 0.32. Okay, and 0.44 if you want it to look like mine. So we're going to see how this is generated, this Julia set is generated in section 7.4. But for now, I just wanted to show you the infinite detail so that I can keep zooming in. And not only will you see infinite detail, you'll see a sense of self-similarity. So you see how it looks right now? I'll keep zooming in and you'll see a sense of self-similarity. See how these little bubbles kind of look like they did before? Only I'm zooming in on them, and you keep zooming in on them, and you see the little bubbles. I'll just pick another one and keep zooming in. And there's infinite detail. I'm limited only by how much my Apple tablet can manage, and self-similarity on numerous scales. You can just keep zooming in there and keep seeing. And see, it kind of looks like what I started with. But here I am way zoomed in. I'll zoom back out again. So infinite detail and a sense of self-similarity across different scales. And make it back the way it was. So this is the original picture. Little. Well, that's one fractal type that we're going to look at, the family of fractals called the Julia set, and the Mandelbrot set we'll see as well in 7.4. I have then an app for those of you with Androids. So the app for Androids is L System Studio. Let's see if I can make that bigger. L System Studio right there. Okay, if you look that one up, that one allows you to make your own fractals. So instead of blowing up the Mandelbrot set or the Julia set, you can make your own fractals. So if you have an Android, you can download the L System Studio. And the way that it works, I'll show you how it works. Well, it uses a very simple language. So we have a few commands. We have F for forward, and then we have plus for turn right. We have minus to turn left. And then we set our angle of how we want to be turning left or right. So for example, if I were to say F, I would go forward. And then if I were to go plus, I go to the right. Actually, I'd turn. I have to do the F to actually go forward to the right then. And then if I go left and left, my direction will turn from going this way, it'll turn back to straight. But if I do two lefts, instead of going straight, it'll go back the way the opposite of the way I was. And this movement of actually drawing there would be another F. And then I can go right again, turn right, and go forward. So this sequence, this little kind of hat-shaped thing, is done by F plus F minus minus F plus F. So we did forward, turn right, forward, turn left, two angles, forward, turn right, and then move forward. Okay, so this is L System Studios that lets you actually make your own little computers up. Let's look at some samples. Okay, so here's this one. This one, you move forward, then right, forward, then right, forward, then right, then forward at 30-degree angles. And then, here's where the fractal part comes in. Every F is going to get turned to this. Every little line segment is represented by F. Every little line segment is going to get turned into a 2 line segments forward, turn right, go forward 1 line segment, go right 2 times, go forward, go right, go forward. Let's see what that does. Okay, so here's the first, it's too bright. I can't see it. Let's see if how can I make it less bright? Does that help? Oops, almost. There it is. A little bit more. There we go. A little more. There. Okay, so that's the first iteration, and now every one of those line segments, when I hit plus, every line segment's going to get changed to the next iteration. Okay, and then I hit plus again, and every line segment gets changed again. And you can keep hitting plus, and every line segment gets changed to what the directions had. Here, let's go back to another one. I kind of like this fractal plant. This one's more complicated. They have more complicated rules, but that's okay. We don't have to do it. We can just look at it. So let's make it go. So here's the first iteration, and now every line segment's going to get changed with the next iteration. Okay, and it changed it there. Every line segment gets changed again. Keep doing it more and more iterations. So every line segment is getting changed to the new pattern. And we can do this as often as we like. So we see infinite detail here. Let's actually make the one that we had described. So we'll click new and put this one in right here, okay? So the axiom is to take f, that's the rule, f plus f, so forward, turn right, forward, minus minus, so left, left, where's minus, 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 then go forward, then turn right, and then forward. And then the rule is to take each f, each line segment, and change it to this. So I'm going to copy this and paste it down here. So every line segment after the first time, every line segment is going to get changed to this. It's going to get changed to itself, in fact. Whoops. Oh, I got to give it how many degrees to turn when it turns 60. Okay, so there's the first iteration. And then the next one, changing every line segment to this new line segment. This one has a name. It's called the Koch curve, and we're going to learn to draw that one. So 2 different systems for looking at or for making fractals. I hope you're able to have fun with one of those. We're going to go to 7.2 and learn to make some of these fractals. What time is it? I think we have time, right? Oh yeah, we have time. Okay, so we're going to...
Can you keep on the slide for a little bit?
You want to see the site again? Do you have an Android?
I have an iPhone.
An iPhone? Okay, so this one I don't think you can get on the iPhone. Okay, you can only get the Fractal Factory one. That one's on the iPhone. I couldn't find one that was on both. Anybody have any other questions? Okay, then let's go to 7.2 and we'll see about...
Can you get it on your computer too?
That's a good question. I don't know if you can get it on your computer.
There's a Fractal Machine website.
There is a Fractal Machine website? Oh, very nice. Does it work pretty close to what we were doing?
No, not really.
Oh.
But it does have the shapes.
Oh, so it's a Fractal Machine instead of Fractal Factory.
Yeah.
Okay. Okay, thank you for finding that. I'll write that down and look at it later. Fractal Machine. So there is no class activity for 7.1. In 7.2, we'll be making some fractals. So the question in 7.2 that we start with is, how do you turn a triangle into a snowflake? Well, it's by doing this process over and over again. So we'll need a full sheet of paper for this. The life lesson in this section is to explore ideas by carrying them to the extreme. So when you keep doing those iterations over and over again, you're carrying those ideas to the extreme. We've actually seen that life lesson in other sections. So you'll need, you're going to start with the Koch curve. And you need a full piece of paper for that, and your ruler. So I'm going to use the centimeters on my ruler. You can use inches if you prefer, but I think centimeters are nice. And we're going to use numbers divisible by 3. So let's use 18 and make a line that's 18 centimeters long, except we're going to make it in 3 pieces and we're going to leave the middle piece out. So we'll make a line that's 6 centimeters long, then we'll leave a blank for 6 centimeters and draw another line that's 6 centimeters. So whatever you're doing, whatever measurement you use, leave out the middle third. Okay? Leave out the middle third. Leave the middle third out. And what we do with that middle third is we draw a point. If you have your compass with you, this will be easier. If you don't have your compass, it's a little hard. Because now what you want to do is you want to make a point here that's, if you use 6 centimeters on each side. So you want to have 6 centimeters here and 6 centimeters here meeting at the top. Well, it turns out you can do that perfectly with a compass. If you do have a compass, you put it, you set it to your 6 centimeters and draw a little line, an arc like that, and then draw another arc. And where those two meet, that's 6 centimeters, because you measured off 6 centimeters, so that's what you have here. If you don't have a compass, you're going to have to just try and get 6 centimeters as best you can. This is our first iteration, or stage 1. So you have your first stage, and now we're going to do the next stage, but first we make sure everybody gets the first stage. So we're going to do by hand what the computer was doing, and that is to draw the next stage as a reduced form of this on each line segment. So we're going to shrink this down so it's 6 centimeters and put it here, 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 and here. Okay, so shrink this whole thing down. So now this time, as we sketch it, we'll sketch stage 2 above. So the first 6 centimeters now is going to have a blank in it. Okay, it's going to have a blank in the middle. So we'll have the first 2 centimeters, then 2 centimeters where we're going to draw the little peak, and then the last 2 centimeters. Same thing at the right side. Okay, so between 12 and 18 centimeters. So from 12 to 14 you have the line. From 16 to 18 you have the line, and you have a little blank there. And we're going to draw the little peak. in between. So we're shrinking down stage 1 and putting it on each of these 4 line segments that we had drawn. So again, if you have a compass, this stage, this is pretty easy. I wish I had reminded you to bring a compass. If you don't have a compass, just draw 2 centimeters up. Okay, so we shrunk down stage 1 and put it on the first line segment, and now we're going to do that with the right hand line segment as well. And we still have the middle to do, okay? So once you get the right and left line segments replaced with diminished stage 1, we go ahead and do the middle 2. So take your ruler or your compass and measure off the 6 centimeters up right here. But remember, don't just draw a straight line. You're replacing each of those line segments with stage 1 shrunk down. So replace each of these line segments with 2 centimeters and 2 centimeters and then a 2 centimeter point. So we're doing what your computer will do for you, but we're doing it by hand so that you can get a feel for how these are done and how you get infinite detail. So I'll come around and see how you're doing after this stage. And this is one of the things I will ask on a quiz that you draw. Okay, you should be able to draw a Koch curve on a quiz. So I'll come around and see how this is going for you. Raise your hand if you're stuck. If you're just working with a straight edge, I would expect it to be a little trickier and not quite as very as neat. Yeah, now we're going to take one of these and replace it with this again. So we'll just take two like that. Well, so you're working with IE, you did pretty good with that, I'd say. I think you just might have thrown an extra piece. Oh no, I didn't, it's just that these came out closer. But again, you don't have a ruler. Oh, okay, that's nice. Okay, so we're going to take each one of these now. Just put this little shape on them. try to get that information later Well, let's go ahead and draw the third stage. So that was stage 2. Now we're going to draw the third stage. So each one of these line segments, how many line segments do we have now? Does anybody else count 16? That makes sense, right? Because there was 4 here, and we took each of the 4 line segments that we had and replaced them with 4 smaller line segments. So we had 4, and then we put 4 for each of those 4, so that makes 16. Well, we're going to do that again now. We're going to take this down and shrink it down and put it on each of these 16 line segments. How many line segments will we have then? You might need your calculator. Well, yeah, 64. 4 times 16, or 64. So let's go ahead and sketch. Now let's see. These are 2 centimeters. So we're gonna have just a little less than 1 centimeter on each of those. This is going to be tricky. Okay, so we're going to have the first 6 centimeters are broke up into little, so they're not, you don't actually draw 6 centimeters, you draw a little less than 1, a little less than 1, 4 times for the flat part on the bottom here. And I'll go over to the right hand side and do the same thing. So that was between 12 and 18. So I started a little more to the left this time, so mine's not lining straight up. But now between 12 and 18, so a little less than 1. Between 12 and 14, I'll make 2 of those, a little less than 1. And between 16 and 18. So you know what? If you put little labels down, that might help. There. So 0 to 6, 12 to 18. And I'm just going to hand draw the little points because that's getting kind of crowded here. Okay, so we have little points in there. So between 0 and 2, I have my smaller stage 1 drawn in. Between 4 and 6, between 12 and 14, between 16 and 18. Now I can finish these outer edges, these outer wings. Go ahead and draw that. Where that's going to go. You have little 2 centimeter points that you're replacing with a stage 1 coat curve. So I'm doing my outer wings first, and then I'm going to do this middle part that rises up. So between the 6 centimeter and 12 centimeter mark. So that's going to be another complicated thing to draw. So we have 1, 2, 3, 4 quote curves on each side of that point in the middle. 4 smaller quote curves. So the parts you draw off to the side right here, those are exactly what you're drawing in the middle. So the way I did it was to do these two and then these two, okay? And then I still have the points to do. So the points are going to have their own little stage 1 quote curve on them. So I still have to do 4 more little stage 1s. So this is one of the things that take practice, and so it's worth more points, okay? Things that take practice are worth more points because you need to practice them. So making 64 line segments is not simple. The original fractals were not made with computers. So you're doing what would have been done by hand when it was first discovered. I'm not sure if the quote curve is one of the originals, but fractals themselves were done without computers first. Even those ones that I showed you on my Apple iPad, which were so colorful. So 64 little line segments because we replace each of these 16 line segments with a reduced 4 line segment piece. Let's see it in our textbook once. Here's some higher iterations. Okay, we did up to here. We did 1, 2, 3 stages. Sometimes the first stage is called stage 0. Sometimes it's called stage 1. On the quiz, I would just say draw 2 more stages, so you didn't have to worry if it was stage 1 or stage 0. Just draw 2 more, 1, 2. This would be the 4th stage, 5th stage, and it just keeps going on. If we could zoom in, we'd see more and more. Now, can you see the self-similarity? harder to see on the stages we drew, but what part of this graph, what part of this Koch curve looks like the whole Koch curve if you zoom in a little bit? One of the things you'll need to be able to do is to circle what parts of the fractals look like the whole fractal. So let's look at this shape. Which part of the fractal is similar to the whole fractal? So this is your completed one that goes on forever if you were to zoom in. Which part of it looks like the whole thing on a smaller scale? How do you describe that? Okay. Does this part look like the whole curve on a smaller scale? The part between my markers? Yeah, it does. This looks like the whole Koch curve on a smaller scale. How about this? Does this part look like the whole Koch curve on a smaller scale? Well, yeah, I'm trying to make it look like it. What about this peak? If I grab that peak, does that look like the whole Koch curve on a smaller scale? That would be a no. It doesn't have the wings off to the left and right. Okay. What if I go out to here? Does this part at the top look like the whole Koch curve on a smaller scale? Yeah, I see some heads nodding. Yes, it does. It has the two wings and it has the middle peak. Okay. So fractals have a sense of self-similarity on different scales, and computer-generated fractals have an infinite detail as well. We're going to go ahead and call it a day here, and we'll come back to section 7.2 on Friday. I'll see you then. Yes. I think so. What does it say for class activity? Oh, the Koch curve? Oh, okay. Then take a picture of this, please, and upload it for your 7.2 class activity. Thank you for reminding me. I can come around and help you if you're stuck.